So welcome guys to my YouTube channel Rare Science Simple, and let's make the science simple. And today we are going to cover the topic of allele and genotype frequencies, normal distribution, which is also known as Gaussian distribution or the bell curve, and the z-score. So first of all, we are going to understand about the allele frequency. So what is the allele frequency? Allele frequency is the proportion of the specific allele in the population, and it is calculated by dividing the number of times an allele appears in the population by the total number of copies of all alleles at a particular genetic locus. So if you suppose have the number of individuals, AA individuals, you need to just multiply it by 2, and whatever the number of heterozygotes, you can keep it like this and divide it by 2n, which is the n is the total population. And why we are multiplying it by 2 is because every gene has 2 alleles. So what is the AA? AA is the number of homozygous genotype with that allele. Capital A small a is number of the heterozygous genotype with that allele, and n is the total number of individuals. And why we are multiplying it by 2 is because each individual carries 2 alleles per locus, and that's how you can calculate the allele frequency. Similarly, how can you calculate the genotype frequency? Genotype frequency is the frequency of the individuals in a population that have a particular genotype. So GF is genotype frequency, which is the number of individuals with a specific genotype divided by the total number of individuals in the population. So with this note, let's try to solve this problem, where we are saying that the population carries 400 members, and in these members there are plants which are red, which is 165, 190s are pink, and 45 is white. Because the flower color reveals the genotype, we may add further the sample of 400 includes 165 capital I, which is a red genotype, 190, which is a capital I, small I, which is a pink genotype, and 45 small I, which is the 45 genotype. The observed number of I and I alleles are therefore you need to calculate. So you can calculate it by the number of ways. So first of all, one way is how can you calculate a genotype frequency? As you know, the number of individuals, if you see this particular formula, so number of individuals divided by the total number of individuals. So you can do it. Number of individuals which are red, number of flowers which are red is 165, and total number of flowers are, let's say, 400. So genotype frequency of the capital I genotype is 0.4125. Similarly, you can calculate there are 90 pink, so, and the genotype for the pink is capital I small I, so the genotype frequency of capital I small I is 190 by this one with 400, which is 0.475. Similarly, the small I genotype frequency will be 0.1125. So in one way, what you can calculate, you just take the 0.4125, and because you are calculating the frequency of capital I allele, and in this particular genotype you have the capital I and small I both, so you need to divide it by 2. So and therefore the allele frequency of the I allele will be 0.4125 plus 0.475 by 2. Similarly, for the small I, you have the small I frequency, which is 0.1175, and in this capital I small I, you need to divide this frequency by the 2, because this has equal proportion of the capital I and small I. So divided it by 2, and you will get the frequency of capital I and the small I allele. This is the one way of calculating the allele frequency. In the another way, how can you calculate? You have AA individual, which is a capital I individuals, which is 165, and you have the 190 capital I small I individuals. You need to keep it like this, divided by 2, and the number of individuals are 400. So you can calculate the frequency of I allele is 0.65, and as you know, P plus Q is equal to 1. So we can write here that P plus Q, the frequency of P allele and Q allele is 1, or you can say here, you can say I and I allele is 1, and you know the frequency of I allele is 0.65. So you can calculate the frequency of I allele, which will be 1 minus 0.65, which is 0.35. Okay. You can also calculate the frequency of the small a allele by this formula, where you can write 2 into AA plus AA by 2n. So you know the number of II, you can say, plus capital I, small I by 2n. So you know small I is 45, capital I, small I is 190, divided by 2 into 400. So if you will calculate, you will get the 0.35. And but the best thing is to do it by this. If you know the frequency of one allele, you can simply calculate the frequency of P allele. P is the frequency of one allele and Q is the frequency of another allele. Okay. So in this way, there are two ways by which you can calculate the allele frequency. So P plus Q is equal to 1, frequency of P allele, and Q is the frequency of second allele. Here the one allele is capital I and the second allele is small I. Now with this note, can you calculate, can you solve this problem? Try to pause this video and try to solve this problem. So here you can see you have sampled a population in which you know that the percentage of the homozygous recessive genotype is 36%. So P square is giving 0.36. So you can calculate P, which is equal to 0.36, which will be, if you do the under root of 0.36, let me do that. So 0.36, so it will be 0.6. So P is 0.6. So Q is definitely 1 minus P, which will be 1 minus 0.6. It will be 0.4. So here you can calculate the dominant genotype, which is PP. So it will be 0.6 into 0.6 is that going to be the frequency of capital P, capital P. Capital P, small p is going to be 0.6 into 0.4, and similarly small p is going to be 0.4 into 0.4. And if you know the per population number, you can actually calculate the number of individuals. For example, if you know initially in a population there are 100 individuals, so you need to calculate, you need to multiply it by 100 and you will get the number of individuals. Okay, so it, for example, you will be getting 36, 24, and yes, you need to divide it by 2 PQ. So because you know there are always AA, 2 AA and small a. So if you are calculating the number of heterozygotes, you need to multiply it by 2. So you will be getting 24 into 2, which will be 48, and 16. So if you will combine them, so it will be 100. Okay, so that's how you can solve this problem. So this was the problem that come in the CSIR 2024 only, where they are saying that the cystic fibrosis is a recessive disease and 0.20% population is having the cystic fibrosis. So calculate the heterozygotes. So you know they have given the the Q square they are giving 0.20 by 100. So if you do this 0.20 by 100, which will be if you will do that, it will be 0.002. So Q is equal to under root 0.002. So we can do 0.002, sorry, under root 0.002, which will be 0.044. Now you can calculate the P. P is equal to 1 minus Q. So you can minus it 1, minus 1. So 1 minus 0.044, which will be 0.955. Okay. 1 minus 0.044, which will be 0.955. So now they are asking the heterozygote, so they are asking the 2pq. So 2pq is 2 into 0.955 into 0.044. So you can do 2 into 0.955 into 0.044, which will be 0.084. Okay. So this is going to be the these are going to be the heterozygotes, and if you want to calculate the percentage, it will be like 8.4%. Okay, so that's how you can calculate the number of heterozygotes. You can also calculate the number of homozygotes, which will be like p square, which will be 0.955 square. You can also calculate the number of recessive homozygotes, which is q square. Recessive homozygotes, which is q square. So q square is already given, which is 0.002. So that's how you can calculate the homozygotes, heterozygotes, and the recessive homozygotes. Okay, because you know, whenever you are multiplying it by AA is multiplying by AA, heterozygotes multiply by heterozygotes, you in the Punnett chart, what you are going to get AA. If you will write, you will be getting 1 AA and you will be getting 2 capital A small a. So that's how it is going to follow in the population. The number of the heterozygotes will be equal to 2 into PQ, which will be 2 into 0.955 into 0.044, which will be 0.084. So in percentage, it will be 8.4% of the population will carry the heterozygotes. Now this is the question again you can solve, that color white is a recessive and all of the butterflies are 40% of the butterflies are recessive. It means q square they have given 0.40. Q is equal to under root or 0.40. P is equal to 1 minus Q, which will be 1 minus underscore 0.40. And now you can calculate the number of heterozygotes, which will be 2pq, which will be 2 into, if you do this calculation, let me do that then, underscore 0.40 is equal to 0.63 and 1 minus 0.63 is equal to 0.36. So you can calculate 2 into 0.37 into 0.63, which will be 2 into 0.63 into 0.37, which will be equal to 0.4662, or you can say 46% of the butterflies are going to be heterozygotes. Okay. Similarly, if they are asking the homozygotes, so you can also calculate p square. P square will be 0.37 square. So if you will do this calculation, you will be getting 13.69% of the butterflies is going to be homozygous dominant. And similarly, you can calculate the q square recessive homozygous, which will be equal to, again they have already given, which is 40%. So it will be 40%. That's how you can calculate by this, and if you will combine all of these percentage, it will be equal to 100%. For example, 46%, 40%, and 14%, which will be equal to 100%. So here you can see 46%, 40%, and 14%. Okay. Now coming to the normal distribution, what is the normal distribution? Whenever the number is continuous, for example, if you are measuring the height, so there are two kind of variables basically. One is the continuous variable, which is like height. Your height could be like 1 feet, 1.1 feet, or 5 feet, 5.1 feet, 5.11 feet, like this. This is a continuous variable. And the discrete variables are like the whole number. For example, either live or dead. Either you are live or dead, right? Either you are man or woman, like this. Okay, so this is the, in case of the continuous variable, normal distribution is going to be followed, and normal distribution is also known as the Gaussian distribution. Okay, or also known as the bell curve. Okay, so the rule of the bell curve is like this: 68% of the values are within one standard deviation. So let me just do this. With the black I need to do. So 68% of the population is like within one standard deviation. Okay, and if you see the second two standard deviation, it will be 95%. 95%. Okay, and if you are saying the 3, this was like 2 and this is like 3 from here. So from here to here, if you will see, it will be like 99%. So this is one standard deviation. Where is my mark? And this is your 2 standard deviation, and this is your this is your 3 standard deviation. Okay, so what does it mean? 68% of the population, which is 34 and 34, is going to be within one standard deviation plus 1. Here you can see plus minus 1. Then 95% of the population, which will include the 68% also, is going to follow the 2 standard deviation. It's like minus 2, yeah, plus 2. Similarly, the 99.7% of the population is going to follow the 3 standard deviation, which is like 3 and 3, like this. Okay, so this one. So these are going, this kind of curve is known as the bell curve, and that follow the 68, 95 and 99.7 rule. Now what is a z-score? Is a statistical measurement that describe the values relationship to the mean of a group of values. So what is z here is a z-score. X is the observed value, whatever the value you got. Mu is the mean value in the population, and sigma is the standard deviation of the sample. So if the z value is positive, it means the z-score is above the mean, and if the z value is negative, it means the z-score is negative the mean. For example, you can see here your z-score, if you see here, if it is like this, and if this is your mean, and z-score is positive, it means it is above the mean. If z-score is negative, it is below the mean. So that's how this works. And a z-score of positive 1 means a positive 1 st above the mean, and the z-score of negative 1 means negative 1 st standard deviation below the mean. and a z-score of 0 means the score is right on the mean. How you can find out the z-score here? If you see here, this is suppose you got the z-score of 1.9. then how will you find it out? Let's say if you got the value of 1.90, then your z-score is going to be 9.97. If it is 1.91, then it will be 0.9719. If it is 1.92, then it will be 0.9736, and like this. So you can see here, if it is like 1.90, the value is going to be 0.9713. If it is 1.91, the value is going to be 0.9719. Similarly, if it is 1.92, the value is going to be 0.9726, and like that on. And in this example, if I am because I have highlighted the value of 1.96, it is going to be the value is going to be 0.9750, okay, which is the value that you can see here, which is this one, 0.9750. So now with this note, can you calculate this problem? Suppose the population was normally distributed with the mean and standard deviation. What proportion of the score are below 12.5? So you can calculate the z-score, x minus mu by sigma. The value of x, which is 12.5, the mean value, which is 10, and the standard deviation, which is 2. So you will be getting 2.5 by 2, which will be 1.25. And if you can see the value here, 1.25, the value of 1.25 is equal to 0.8944. This one, 1.25 is equal to 0.8944. So now you can write this value here, which is 0.8944, or you can say the 89.44% of the values are going to be below 12.5. And this z-score is very valuable whenever the scientists are performing the clinical trials and measuring the expression of a particular gene in a particular person. Then they can say that that particular individual is having the more expression or the less expression of the gene in comparison to the mean value. Okay. And similarly you can do this formula. You can also solve this problem, which is saying that the mean value of the score was 425 in the SAT test and the standard deviation was 110. What percentage of the students would be expected to score in between 350 to 550? So try to solve it by yourself. For the value of 350, you can calculate it will be 350 minus mean by standard deviation. Then 550, you can calculate the 550 minus this one divided 110. And for this value, you need to see the z-score value from the z table. And I have already done this, so I will just write the values here. So what is going to be the values here is minus 0.6. The value will be like minus 0.68 or 1.14, and the value for minus 0.68 is going to be 0.2483 and 0.8729. So the values in between is going to be 0.8729 minus 0.2483, or you can say 0.6246, which is 62.46% is going to be percentage of the students would be expected to score between 350 and 550. Okay, so that's all about this lecture, and if you like the content of my lecture, kindly do subscribe my channel. Thank you so much.